Hey everyone, happy Monday. Hope you're doing well today. Sorry I can't be with you. Today we're going to be talking about 4.3a, which is about the graphs of f inverse, and f double inverse and how they relate to each other. So getting a little bit deeper into graphing here, we talked a little bit about this kind of stuff when we talked about motion, but we're actually going to go a little bit deeper with it here. Before we get into that, though, I want to tell you a quick story about the mean value theorem, which is what we learned on Friday. I was in Scotland last March for spring break, and they had these signs everywhere on the highway. They've been having a lot of trouble with people speeding in Scotland, so they installed these average speed cameras. And they actually have these in Iowa now as well. And the way they work is they take a picture of you, a picture of your car, and then they take a picture of your car again in maybe like 20 miles, maybe 10 miles, doesn't really matter. But they know the distance between the cameras, and they know the difference in time that passed between the two pictures. And so what they can do is they can calculate your average speed. And so sometimes you see that these are actually called average speed cameras. So what they know is they say, well, you traveled this much distance, so they know your S of your final time, so S of t2, and they know your S of t1, and then divided by t2 minus t1. Usually this is 0, right? And then you traveled a certain distance over a certain amount of time, so they know your average velocity. They know your average velocity. And what mean value theorem tells us is there must be some instantaneous, I should call that S, there must be some instantaneous time c between t1 and t2 where this happened. There must be some instantaneous time where you were going that exact speed. So if that exact speed is, let's say, 10 miles an hour over the speed limit, they know that you were speeding at some point. So they're using calculus, mean value theorem, to be able to catch you speeding, which is kind of cool and kind of mean all at the same time. But that's kind of one of the problems that you had in the homework was kind of like that, and it's kind of cool. So without further ado, let's get into 4.3. So the first concept that they talk about in 4.3 is called concavity. And concavity is told to us by the second derivative. So the second derivative tells us about concavity. And concavity, the way that it's almost always described, is that concave up means it's up like a cup. All right, so this section of the graph right here is concave up because it's like a smiley face. It could hold water if you poured water into it. So that's the concavity. So the concavity is up like a cup right there. It's down like a frown right here. So it's concave down that entire time because we're coming in here. It's looking like we're going facing downward for the graph that whole time. And then the spot where it changes, this is what's kind of confusing to some people. I'm going to give you a way that I remember it later here. But we're concave down this entire time because the graph is facing downward. And then the inflection point happens probably right about there. So that's where the inflection point happens because it changes from concave down to concave up. So that point right there, it's kind of like a flat point in the graph. If you were to put a tangent line in there, I'm going to not be able to draw this very well, but I'll try. If you were to put a tangent line in there, it would change from being above the graph over here to being below the graph over here. It would kind of go through the graph. And that was a pretty poorly drawn tangent line. I'll try again. But it would be kind of above there, and then it would go to below if you drew a tangent line right at that point, at the inflection point. So a graph is concave up if we have a positive second derivative. I'm going to show you why that is in the next slide. And it's concave down if we have a negative second derivative. So this entire first portion of the graph here until the inflection point, that must have a negative second derivative, and then the second derivative over here is going to be positive. And we'll see why that is in a second. The inflection point is where we have that change in f double prime. So let's see here if we can draw some graphs and see why that is. So why? Well, let's take a look at this, and we'll try to draw f prime of x, and we'll try to draw f double prime of x, and we'll see what's going on. So f prime of x is just the slope of our initial function. So it looks like the initial function at the beginning here has a positive slope, and that happens until 0. So at 0 we have a slope of 0. And then it looks like between 1 and 2, like right about here, we also have a slope of 0. Those are the only two spots where we have a horizontal tangent line. So that's our only 0 slopes. So we're going to come down like this, maybe. I don't even know how to do this. So let's come down like this, maybe, and then it's going to, let's see, it looks like it's, so we have decreasing function here, so it's negative for a little bit. And then it comes back up like this, and then it's going to be increasing again from that point on. So we have upwards. Looks like that's like a parabola. Put some arrows on that. Now, the second derivative is the derivative of the first derivative. So we just have to say, okay, well, it looks like this guy is decreasing, so it's negative for a while until this spot right here where we have a horizontal tangent line on the derivative. So we have a 0 right about here, somewhere just shy of 1. And we're decreasing the entire time until that. So we have to have a negative for second derivative until we get to that point. And then it looks like we're increasing after that, so it's going to be positive. So it looks like it actually might just come through like that, like a linear function. So if we look at the concavity, we said it looked like it changed about here. So we were concave down until that point, and then we were concave up. Well, let's look at our second derivative. Yeah, the second derivative is negative until we get to that point, and then we're positive after that point. So second derivative, negative down here, positive after, because we're just looking at the y values. Just looking at the y values here. At this point, we have negative y values. At this point, we have positive y values. So that's where we change, right where the second derivative is 0. That's where we have that inflection point. We change from concave down to concave up. So some things that these derivatives tell us. F prime of x tells us when f of x is increasing or decreasing. So f prime of x, the first derivative, tells when f of x is increasing or decreasing. Increasing or decreasing. And that's by if it's positive or negative. So it looks like from negative infinity to 0, we are increasing. And then from 0 to, I don't know, about 1.25, something like that, we are decreasing. That happens here. And then we're increasing after that. There we are. The second derivative tells about the concavity of f of x. So we look at this, we have a concave down graph up until we get to that inflection point, and then we have a concave up graph after that. It tells us also the slope of f prime, but that is something we're not usually concerned about. We're mostly concerned about what's happening on the graph of f of x. Cool. So I've been thinking about this. I thought about this all summer. I thought there's got to be a better way to talk about concavity, because this whole up like a cup, down like a frown thing, I think it can be confusing, because if you have a graph like e to the x, this is f of x equals e to the x power. This graph is concave up on its entire domain. Concave up on its entire domain. But if you say this is concave up like a cup, anywhere you put water into this is going to slide off, right? It's going to slide to the left. So I think I have trouble saying it's up like a cup. So what I started thinking about was, okay, let's say you're driving a car. There's a car, 4 wheels, lovely. I'm really good at art, I know. So this is our car, and if you drive left to right on a graph, any time that your car is turning to the left, you're concave up. So if you're turning your car to the left, it's concave up. If you're turning your car to the right, that's when you have a graph that is concave down. So let's try it on their graph that they gave us. So here's our car. There we are. I don't know who's in the car. Maybe Mr. Fransky and, I don't know, Mr. Simpson. Sure. There's Fransky and there's Simpson. Okay. So we're driving along, and Mr. Fransky's like, oh, we're turning to the right. So this whole time we must be concave down. So this whole time we're concave down because we're turning to the right, to the right, to the right. And then, oh, what happens right here? So for those of you drivers out there, if you're driving here, turning to the right, to the right, to the right, that split second is when your wheel is straight. So when your wheel is straight, that's when you have an inflection point. That's kind of cool. So straight is an inflection point, right? And then, for the rest of the time, we're turning left, left, left. And that's where we have the concave up graph. So this entire time, right up here, like our wheel is almost straight, but we're still turning just a little bit left the entire time. So we were turning to the right, we were concave down, and then you're concave up when your wheel is turning to the left. So if you're driving left to right along the graph, that'll always work. Let's try one more like that. If you're in your car here, there we go. So this beginning part, which way are we turning? Well, it looks like we're turning to the right. So that whole time, we're concave up, and this time the up like a cup thing might make sense. And then over here, we're definitely turning right. So we were turning left, up like a cup. Now we're turning right, down like a frown. Where did it change? Where was our wheel straight? Maybe somewhere about here. Okay, so that was where our wheel was just barely straight, so that's where we have that inflection point. Okay. Now we're turning to the right, to the right, to the right, so we're concave down. Over here, at some point, we change to turning to the left. So again, we have to find that inflection point, maybe somewhere about here. And that's where our wheel would have been straight, just barely, just for a second. And now we're turning left, 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 so we are concave up for the rest of the time. Excuse me. So concave up the rest of the time because we're going to be turning left for the rest. Okay, so we had one inflection point, two inflection points in this graph. Change from concave up to concave down to concave up. Cool. Now, this is probably why I started thinking about this. There is a spot on Benton Avenue, which if you're going from the high school over to the community center or something, some people will go up Tracy and then take a right on Benton, take Benton all the way over to the community center. And when you're going around this pond that's just after Tracy, I always think about inflection points because this is where you driving this way, where the arrows are, and you start by turning to the right, and then you make a quick change right about here to turning left, and you make a quick change right here again to turning right. Those are where the inflection points are, right? We change from something that's concave down, where we're turning to the right here, if this was like our x and y axis maybe. So we're concave down, and then we turn concave up, and then we go back to concave down. And there was one day I drove around this pond like 3 or 4 times just thinking about this, about how the concavity was changing. I am not even kidding that I did this. And what I'm thinking is, hey, maybe you guys can do this too. So, let's see here. Got it over here. Yeah. So the high school is right here. And if you guys go out and take a left, and you drive, and you pass where Tony stands and directs traffic, and you take Tracy across the highway, and you go all the way up to Countryside School, and then you take a right onto Benton right here. That is where this thing happens. So, oh, that's not what I wanted. I wanted to zoom in. That's okay. It'll still work. So, if you head over to Benton, right up here, and you drive around this pond, maybe once or twice, and you bring someone with you to take a video on a phone or a camera or whatever you've got, of you driving through and mentioning, just watching the steering wheel, just turning through here, and when that wheel is straight, I want you to say, hey, that's an inflection point. All right? So, drive around the pond, maybe go once this way and once this way, something like that. Edit your video. You guys are all good at that stuff. And maybe we'll show it to the class. So if you want to email it to me or somehow get it to me, that'd be just fine. And we'll take a look at your inflection point video and talk through, hey, yeah, I'm turning right at this point, so it must be a concave down graph. And then it's straight for a second. You say, oh, that's the inflection point. And then you're concave up while you're turning left. And then when you hit that other inflection point, your wheel is straight. You're going to be concave down again. Kind of cool. So give it a shot. We'll see how it goes. All right, let's get back to our lesson here. Where are we? Calculus Monday. There we are. All right. Excuse me. Okay, so moving on. Let's try an example. So first we're going to look at when this graph is increasing and decreasing. So according to our chart we had before, where we were drawing the derivatives, f prime tells us when f of x is increasing or decreasing. So let's try that with our example here. So we have this function, f of x is x squared minus x minus 12. So let's take the derivative. F prime of x is going to be 2x minus 1. So when that is greater than 0, we're going to have a graph that's increasing. When it's less than 0, it means that f of x is going to be decreasing. So let's see if we can figure out a little number line for f of x here, or f prime of x, excuse me. So this is f prime of x. And we're going to figure out when it's equal to 0. So 2x minus 1 needs to be equal to 0, so 2x equals 1, x equals 1/2. So 1/2 is our only 0 here, 1/2. And prior to 1/2, so if we try something less than 1/2, like 0, we plug in 0 here, we get -1. So we have a negative first derivative prior to 1/2. After 1/2, let's try like 1. 1 times 2 is 2, minus 1 is 1, that's positive. So we have a positive first derivative after that. Now 1/2 is the only 0, so it can never change anywhere else. The only way that the derivative can change is if it goes through the graph, or sorry, goes through the axis, or if there is some kind of a place where it's not defined, but we have a linear graph here, so it's definitely going to be defined everywhere. So this means that our function f of x is increasing on 1/2 comma infinity, because that's where our first derivative is positive, and it's decreasing from negative infinity all the way up to 1/2, because that is where we have a negative first derivative. Okay, so all we did here was we took the derivative, we found the critical point, which was just 1/2. That was the only place where our derivative was 0. And we tested the point on the derivative function because we said, hey, if our derivative is negative, we're decreasing. If our derivative is positive, that's where we're going to be increasing. And that's all we had to do. Kind of cool. Now let's see what's going on with the concavity of this graph. So we knew that f prime of x, we just found that. That was 2x minus 1. So our second derivative, f double prime of x, is just 2. Well, that's kind of a weird second derivative. It's always 2. So the second derivative of this graph is always 2. Well, we know we're concave up if f double prime of x is positive. So if f double prime of x is positive, we're concave up, and it's concave down if it's negative. Our second derivative is always 2. So we're always concave up on negative infinity all the way to infinity. And it's never concave down, because our second derivative doesn't even depend on x. It's always 2. So let's see what's going on with this. If we go over to our Desmos here, I've got these lined up. So this is the graph f of x equals x squared minus x minus 12. Okay, so this is that graph that we were talking about. And we see that we do indeed change from decreasing to increasing at 1/2. We can see that also by looking at the first derivative. So the first derivative, we see, just like we said, it was a line. It's negative up until we get to 1/2, and then it's positive after that. So that shows us the relationship here. We're decreasing until we get to 1/2, and then we're increasing because our first derivative changes from negative to positive. Let's take a look at the second derivative. We said it's always 2. And if you did have your little car on here, yeah, you'd be turning left the entire graph. You never turn right at all. There are no inflection points. The whole time the graph is concave up. And that's it. Cool. All right. Here we are. So let's take a look at another example. This one, we're trying to find we're starting with increasing, decreasing again. This time we have a quartic function, x to the 4th minus 10x squared plus 9. So to find where it increases and where it decreases, we should use the first derivative. If you want to pause the video right here and give this a shot yourself, you can. All right, welcome back. Let's see what happens with our first derivative. So our first derivative is 4x cubed minus 20x. And the plus 9, the derivative of that's just 0, so we have it right there. So 4x cubed plus 20x, I can factor an x out of that. It's even a 4x. 4x times x squared minus 5. We want to know when that's equal to 0, because that's going to find us our critical points. So that's equal to 0 at, let's see, so if 4x is 0, that would be 0. So 0 is a critical point, x equals 0. X squared minus 5 is going to be 0 at positive root 5 and at negative root 5. So we have 3 critical points, and let's mark those on our number line here. Whoop, negative root 5, not root x, Fransky. There we go. Here's 0, and here is the square root of 5. So now we have to test points before, between, and after each one of those. So prior to negative root 5, let's say like, I don't know, so square root of 5 is between 2 and 3 somewhere. So let's say that we try like negative, I don't know, negative 7 or something. So if we do negative 7, this guy out here is definitely going to be negative. And this guy in here, so negative 7 squared is positive 49, minus 5 is positive. So we have a negative times a positive, which gives us a negative number. In between negative root 5 and 0, let's try like negative 1. So we plug negative 1 in here. Negative 1 times 4 is negative 4, so it's a negative number. Negative 1 squared is 1 minus 5 is also going to be negative. So we have a negative times a negative, which gives us a positive number. Between 0 and root 5, number good in there would be like 1. 1 times 4 is positive. 1 squared is 1 minus 5 is negative. So we have a positive times a negative, which gives us a negative there. And then after root 5, like something like, I don't know, 8. 8 times 4 is positive. 8 squared is 64. Minus 5 is also positive. A positive times a positive would give us a positive number there. So this was f prime of x that we graphed here. Oop, that's a bad f. So f prime of x, and we saw that it went from negative to positive across these critical values. So we are increasing on negative root 5 to 0. We're also increasing on root 5 up to infinity. We are decreasing on negative infinity to negative root 5, and also from 0 to positive root 5. And we see that because this is where f prime of x is greater than 0. This is where f prime of x is less than 0. And we saw that by testing our values between the critical points on our function. So you probably know what's coming next. We're going to see when this guy is concave up and when it's concave down. So to do that, I'm going to borrow my first derivative that we took on the last slide. We knew that that was 4x cubed minus 20x. So I'm going to take the second derivative, f double prime of x, which is going to be 12x squared minus 20. And we want to figure out when this thing is equal to 0, because that's when we might have a concavity change. So we might want to factor this again. So if we factor out of 4, we'll have 4 times 3x squared minus 5. We don't know when that's equal to 0. So that 4 will never be 0, so this factor in here, 3x squared minus 5, has to be equal to 0. So we have 3x squared equal to 5. That means x squared has to be 5/3. Square root of both sides. X could be plus or minus square root of 5 over 3. I want to rationalize that. Root 3 on the top and the bottom. So that looks like it's root 15 over 3. So 15, let's see, that's almost 16. So root 15 is almost 4 divided by 3. So that's almost 4/3. Make our number line here. This is plus or minus. So here is our f double prime of x. So we have negative root 15 over 3, which is almost negative 4/3. And then we have positive root 15 over 3, which is almost positive 4/3. So we're going to test some points before, between, and beyond here. So if we try 0, 0 is smack dab in the middle. Plug 0 into our second derivative here. It looks like 0 squared is 0, minus 20 is a negative 20, so that's going to be a negative number. Something less than negative 4/3, we could try like negative 2, because that'd be 6/3. So let's try negative 2. Negative 2 squared is 4, times 12 is 48, minus 20 is definitely positive. And then something beyond, like, I don't know, 2. 2 squared is 4, times 12 is 48 again, minus 20 is also positive. So it looks like we change from concave up to concave down to concave up. So we are concave up on negative infinity all the way up to negative root 15 over 3. Also, we are concave up from root 15 over 3 all the way off to infinity. And that's because that's where f double prime of x is greater than 0. And then we are concave down in between the negative root 15 over 3 up to positive root 15 over 3. Because f double prime of x is less than 0. So let's take a look at the graph again in this and see what's going on. Keep, and back over to Desmos. So let's look at the next set here. So this is the original function. Looks like we've got a quartic. The derivative tells us when it's increasing and decreasing. It's kind of tough to tell here, but it looks like we're decreasing up until this little bump right there. And it looks like that is indeed when we cross through. So we're decreasing until we hit that spot right there. And then the function increases up until here, and that's why our red graph is positive. Our red graph is our derivative here. So it's increasing because the red graph's positive that whole time. And then from 0 down to this little bump right there, looks like it happens at 2.23. That's where we are decreasing. So that's why our first derivative is negative. And then we increase for the rest of the time after that bump right there. So that's why our red graph is positive for the rest of our domain. Look at the second derivative, it'll tell us concavity. Let's look here. Looks like if we had a car on here, it'd be turning left, 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 all the way until maybe about here. So we expect a 0 for our second derivative right about there. That must be that negative 15, root 15 over 3. And then we're concave down until right about here. That must be our positive root 15 over 3. And then we're concave up the rest of the time. So it looks like we have 2 zeros on our second derivative. And there they are. There's our first 0. There's our second 0. Got a nice parabola there. That must be that 12x squared minus 20. And look, it goes right down to negative 20. So that's how these graphs are kind of being related to each other. All right, let's go back to our examples. Here we got one more example. Where are we? Here we are. So, come on. So let's go to one more example here. Got a trig one. So we got f of x is cosine squared x plus sine x. And we're just looking at 0 pi. I'm trying to figure out when it's increasing and decreasing. So that means we need our first derivative to find out increasing and decreasing. So f prime of x is going to be 2 cosine x, and then we got to change. That's going to be multiplied by the derivative of cosine, which is negative sine. And then derivative of sine is positive cosine x. So let's see if we can clean that up a little bit. Looks like we could factor out a cosine x. So it looks like it could be cosine x times 1 minus 2 sine x. So I did a little bit of a switcheroo there. If you were to distribute here, we would have that positive cosine x, and we would have negative 2 sine x cosine x, and we would end up with the same thing. And we're wondering when that's equal to 0 to find the critical points. So if that's equal to 0, either cosine is 0, or 1 minus 2 sine x is 0. We're looking just from 0 to pi, so we're just on the top half of the circle, right up there. So cosine x being 0 somewhere in there, that only happens up here at pi over 2. So pi over 2 is for sure one of our points that we're going to be concerned with. And then 1 minus 2 sine x, if that's 0, that looks like sine x would have to be 1/2. So if sine x has to be 1/2, that happens over here at pi over 6, and also over here at 5 pi over 6. So let's set up our number line here. Those are the 3 spots we're worried about at pi over 6. And then at pi over 2, and then at 5 pi over 6. So we start at 0 and we end at pi, so we have to check all those intervals in between. So between 0 and pi over 6, well, cosine x is definitely positive over there. And 1 minus 2 sine x, well, sine x is going to be less than 1/2. And something less than 1/2, like let's say like, I don't know, wherever sine x is 1/4, so somewhere down here. So if sine x is 1/4, I'm going to be doing 1 minus 1/2 then. That's going to be positive. So a positive multiplied by a positive, we definitely have a positive there. In between pi over 6 and pi over 2, we could try, I don't know, like pi over 3. So pi over 3, sine of pi over 3 is root 3 over 2. So this would be 1 minus root 3, which is negative. Cosine is going to be positive there, so we have a negative times a positive because it's negative. Between pi over 2 and 5 pi over 6, we could try like, I don't know, 2 pi over 3. So we do 2 pi over 3 there. Sine, once again, is going to be positive root 3 over 2, so that gives us a negative through this factor on the right. And our cosine over here is actually going to be negative now. So we have a negative times a negative, which gives us a positive. And then at the end here, so we're down back to where sine is maybe like 1/4 or something. If sine is 1/4, that'll give us a positive number here. Cosine is still negative on that second quadrant, so we have a negative there. So it looks like we go from increasing, decreasing, increasing, decreasing. So we increase on 0 pi over 6. Also from pi over 2 to 5 pi over 6. And then we decrease everywhere else from pi over 6 up to pi over 2. And also from pi over 6 to pi. That's where we have our increasing and our decreasing. I think we have a picture of the graph here. It's probably going to get caught up in my number line a little bit, but it looks like we increase up until we get to pi over 6, and pi over 6, is about 0.52, something like that. And then we decrease down to this minimum right here, which happens right at pi over 2. And then from pi over 2 to 5 pi over 6, we're increasing, and then 5 pi over 6 over to pi, that's where we are decreasing again. It looks like that's what happens with our graph. Kind of cool. All right, let's talk concavity. And since we've got this graph right here, I might as well just take a look and see what's happening. Looks like we're concave down until right about here somewhere. Then we're concave up until right about in here. And then we're concave down. So we're concave down, up, and down again. And let's see if we can prove that using calculus. So we had our first derivative. Our first derivative was cosine x times 1 minus 2 sine x. So we're going to use product rule to find the second derivative. So our second derivative here, that's going to be the derivative of the first, which is negative sine x. Leave the second thing alone, 1 minus 2 sine x. Plus, leave the first one alone, cosine x. Derivative of the inside here is going to be negative 2 cosine x. So when that all shakes out, it looks like we have we have anything positive? Yeah, we got a positive 2 sine squared x. And then we subtract sine x, and we subtract 2 cosine squared x. Now, it'd be nice if we could get these together to be Pythagorean, but this one's positive, this one's negative, so it won't work out. We could maybe get an identity here that it's 2 cosine, or cosine 2x, but that's not going to help us a lot because we still have that sine hanging out there. So we want to know when this is equal to 0. Well, unfortunately, that's not a very happy thing to find. So I'm going to go over to Desmos, so we're actually just steal those values. Keep. So if we go to Desmos, right here, and we have our last function here. So there's the function that originally. Probably zoom in a little bit on that. And we're looking at just 0 to pi. All right, so here's our 0 to pi, very shallow increase, decrease, increase, decrease. And here's the first derivative. First derivative we saw have an increasing function until that's at pi over 6, and then our pi over 2, and our 5 pi over 6. Our second derivative is what we're concerned with now. So look at our second derivative. We see that we cross through, it looks like just past 1, and then we cross through again between 2 and 2.5, somewhere there, 2.139 it looks like. So those are those two values, and this is how you can do it on your calculator. You find that second derivative, you graph it, and you figure out when it's 0. Okay, it looks like it happens at 1.003, and then also at 2.139. So this happens at x equals, gotta make it big, x equals 1.003 and x equals 2.139. So if we make our number line, we have 1.003 and then we have 2.139. Good thing we have 3 decimal places because that's what you need for the AP test. So if we think back to our Desmos graph here, we see that we have a negative second derivative because we have our values, or y values, are below the axis until 1.003. Then we change to positive and then back to negative. So we go negative, positive, negative, which tells us the concavity of the graph. We're concave up in between there, 1.003 to 2.139. And then we're concave down from negative infinity up to 1.003. And also from 2.139 off to infinity. That's right. And the graph we have again here, we see we're concave down until just about 1, then concave up, and then back to concave down. It confirms what we said, and it's the same graph as we had in Desmos. Well, that's all I've got for you today. Sorry, this video got a little longer than I wanted it to. But we have just a book assignment for you, and please do email me with questions. If you ask me a good question, you might even get a video problem tomorrow, and I'll give you a shout out. So hit me up at noah.fransky@edinaschools.org. Let me know what your question is. You want to see one of these problems or anything that you want cleared up from the video, and we can take a look at it. I love you guys. That's why I'm here. Have a great day. If you are looking for something that's a little bit less calculus oriented and a little bit more logic, I've got a puzzle for you that I actually had up on the screen for some of my classes last week when we were doing a test, and they found it pretty interesting. So you can read through it. The basic idea here is that there are 1,000 pirates and they're all numbered. They know their number. So pirate number 1 knows he's number 1. Pirate number 823 knows he's 823. They have enough gold to split evenly among all of them, so maybe like 1,000 factorial pieces so that you could split it evenly among any number of pirates. But if there were fewer pirates, that would mean there's more gold to share. Yeah, that's great. So they're going to vote on whether or not to kill pirate 1,000. The majority rules, so if they can get 501 people to vote to kill that pirate, they'll kill him. If they do, then they'll vote on 999, and then 998, 997, so on and so forth, until they get to a place where they can't get a majority rule. So assuming that all the pirates are perfectly logical, greedy, and they don't want to die, how many pirates will split the gold? So a good place to start here is, okay, well, if there's one pirate left, he gets all the gold. If there are 2 pirates left, the pirate number 2 will vote to save himself, pirate number 1 will vote to kill him. So they would split the gold there as well. And just kind of keep working your way up and see what would happen as you go. The result is kind of cool, and I'll tell you in tomorrow's video. So I love you guys once again. That's why I'm here, and good luck with your homework. I'll see you tomorrow.